Hello again, it's Cliff here from Down Under. This video I want to do a bit of a discussion on design, a fascinating subject to me. Good design is usually a balance between conflicting requirements. It's usually a compromise, but there are some very fascinating exceptions to that. And I hope I'll be able to give some graphic examples to explain what I mean. In case some of you find that rather philosophical subject of design not your thing, I'll also be going over material strength and stiffness, and that might be of interest to you. Alright. Well, I've just bought myself a precision level. I've always wanted to get one of these. This is not a really expensive one, but that doesn't really matter because the way these levels work is that they are comparators rather than absolute measures, and they can be sort of self-calibrated because you just make the level adjustment by rotating from one side to the other until you've got the bubble in the middle. These are really sensitive instruments. This will measure 0.02 of a millimeter per graduation over a meter. So that's less than a thou over a yard. I like that. Really, you're in control of surfaces, and very good for setting up a machine tool and checking that the castings aren't twisted. I look forward to getting onto that some stage in the future. Anyway, what I wanted to talk about here was a very interesting subject I've been mulling over lately, and that is design balance. You know that when you're designing something, a decision has to be made that is usually a compromise. See if I can explain that. You know, every aspect of the design is usually a compromise. It's a balance between, for example, being light and being strong. You can't have it too light or it won't be strong enough. You can't have it too strong or it won't be light enough. Is that coming through okay? And just about every aspect of design is a compromise. It's a compromise between conflicting requirements. And it's not very often you come across a design situation where it's not a compromise, where actually you have complementary requirements. And that brings me to the subject of what I'm doing at the moment, which is I'm doing another production run of these styluses for the ITTPs, and doing a big batch of these at the moment, spark eroding the holes in the balls and grinding the stems and so on. And this is a really interesting subject because these styluses are actually not a design compromise. Very occasionally you strike that in design. An example of a common mechanism that's not a design compromise but is a complementary design is, I think, is that of step pulleys and V-belts. You know, when you want to run the cutter slow and you need a lot more torque, the driven pulley is fortunately bigger, and so it has a bigger surface area, a bigger circumference, and it has a larger diameter, and it's less likely to slip. How convenient! Usually things are the other way around, and when you want to get one lot of improvement, you get some other downside to it. So it struck me when I first discovered the design of, when I was very young, of the step pulley system. I thought, hey, that's not a compromise. That is actually a complementary situation. And it's no wonder they're so commonly used because they work so well. Anyway, that's a good example of the exception to the rule. That is not a design compromise. Okay, so while I'm trying to give a bit of a background onto what design, decision, compromises and balances are about, it's because it's a good introduction to a very interesting eureka moment I had when I was designing these impact tolerant touch probes a couple of years ago. You know, a classic touch probe works by having a fragile self-sacrificing stylus. And when you crash, the stem breaks, and it protects the inside of the touch probe. And that is a classic compromise, because on the one hand, it has to give way to save the insides of the probe. On the other hand, it has to be stiff enough so that you don't get too much flex and lose accuracy due to pre-travel variation. And flex of the Stylus stem gives you a real problem with accuracy, because you always get pre-travel variation with these 3 swing arm probes. Anyway, I thought, wow, if I could have a design that instead of being sacrificing the Stylus assembly retracted inside the probe with a large travel of retract. If you're interested in the subject, I've done a series of videos about 2 years ago based on the Tormac SPU40 touch probe, and it has a fragile self-sacrificing stem, and the way it protects its internals by being self-sacrificing. Some of you will think, well, does it really matter if the probe flexes a little bit? You just enter an effective diameter that takes into account the flex, and that can't be done, unfortunately, because they have 3 swing arms inside these probes, and 3 is that classic tripod number that gives an even contact I've talked about in leveling machines. And when you've got 3 swing arms, unfortunately the load to break the contact in one direction is different from the load to break the contact in the other direction. I go over this at length in these videos a couple of years ago, so I won't go into it now. But that means you get a variation of flex, and that's called pre-travel variation. So the stiffer the stem, the less is the pre-travel variation, and the more is the accuracy. And that really made the idea of a retracting probe with a very strong, stiff stem very appealing. Then we could design the stem to be optimum strength and stiffness, and it would have less flex and therefore less pre-travel variation. And so suddenly all the little lights came on and bells rang, and I thought, right, that would be beautiful. That would be one of those rare cases where you get a complementary design decision. And so that headed me off in the direction of the impact tolerant touch probe. And that meant that the design requirements, for example, on the stem, were no longer to be weak enough to be self-sacrificing, yet stiff enough to be accurate, which is almost impossible. They now just had to be strong enough to be accurate and slim enough to allow you to use it on relatively small jobs, to have a relatively small stylus tip diameter. So that meant, well, a hammer has a 4mm ball, and so you need a stem a little bit less than that and ground down to a little bit of taper. But those are easy and easily satisfied requirements, and a nice gentle compromise compared with that of a self-sacrificing stylus design. So then I had to look into, well, what is the optimum material that is slim and yet really strong and really stiff? Oh, I'm raving on about the theory of it a lot here, I know. So I'm going to go now and do a little practical test to show you something that may be a little bit more interesting to follow. So on the design of these styli stems, they need to be, on the one hand, have high strength so that they don't bend under impact, under a crash. And on the other hand, they need to be stiff so that you don't get much pre-travel variation. Now remember, they are different qualities in a material. Strength is the maximum stress applied before permanent yield or permanent deformation, and stiffness is how easily a component bends under load while still returning to its original shape. In other words, the elastic deformation zone. So I'll do a little practical test now and show you the difference of those qualities, hopefully fairly clearly. Okay, so what I've got here is 3 different types of steel that I could make the Stylus stems out of, and I'm going to do a little test. I've yet to try it, so we'll find out as we go how well it works, to show you the strength and the stiffness of each of these types of steel. So I'm going to hook this scale up on here and pull it and measure the flex and how much stiffness it has and how much strength it has and what are the different zones. It'll just be fairly basic, but it should be a graphic illustration of the difference between one type of steel and another type of steel. Okay, so I put my sample of steel in the vise, stuck it out 40 millimeters by measurement, put a pair of vice grips snapped on the top for safety, and I'm just going to pull on it and see roughly what the zones are of stiffness and strength. So let's have a look. Hopefully you can see that okay. So I'm pulling on about 10 kilos there, and it's pretty well returning. 10 kilos. This is a sample of mild steel. Now I'll pull a bit more, I'll put on 15 kilos. Now see that it's taken a permanent set. In other words, it's reached its limit and it's permanently yielded at 15 kilos. So that's its yielding point, 15 kilos. Now we'll set up for another material. Okay, now we've set up the next test piece. Now that's a piece of silver steel. Most of you will know silver steel is a high carbon tool steel. It's in its unhardened state, but it's quite a strong type of steel. Let's see what that will stand. Let's start putting a load on it. It's flexing at 15 kilos and returning. 20 kilos and returning. This is interesting. 23 kilos it's going. 24, 25 kilos it's going. And that's its permanent yield point. So it has flex up to there. Okay, so now I'm going to test the steel that I actually use in the ITTP. It's a high quality, high alloy, heat treated steel. And I've chosen that because it has to be able to stand a crash without bending. It's no good having a prang up and having the probe recovering internally without any damage if the stem is bent. So it has to be very strong, and it also needs to be stiff so that you have the minimum pre-travel variation. Okay, let's test the actual steel that I'm using in these probes. So let's first of all see if we can find out how stiff it is, how easily it bends under load while still returning to its original state. This is the elastic deformation. So 20 kilos, it's returning. 25 kilos, it's returning. 30 kilos, it's returning. Wow, 35 kilos. I hope this is safe. 35 kilos, 37 kilos. Has it started to bend yet? Oh, I think it's just starting to go now. I can hear it creaking. 45 kilos, and it's just starting to bend. That is massively strong for a little skinny probe stem. Well, should we test the self-sacrificing stem? No, I'm just kidding. So anyway, you can see from that how it opened up the potential for a big improvement of the stiffness and therefore accuracy of the probe design. So that was a big plus for me, and it really boosted me through that design period. Now I'm sure some of you astute watchers will have noticed that I've been blurring my use of the word stiffness a little bit here. A common misconception about strength and stiffness. The test that I was doing was strength. We're testing the strength of these components, the maximum stress applied before permanent yield. And remember that stiffness is how easily a component bends under load while still returning to its original shape. Not how far it bends, but how easily it bends. I'm just up now in the office uploading those clips I've just taken, and also having a look at some earlier clips of when I was doing the research into pre-travel of these probes. And listening to my earlier workshop clips, I realized that I'm being a bit blurred with the use of the words strength and stiff once or twice. I need to be really careful to be pedantic about this, because the whole point of this video is to understand the differences. And so I'm sorry I've got a bit kind of loose there. I'm so concerned about keeping the dialogue flowing that I'm not really getting the content 100% all the time. What I have been testing down in the workshop is the strength of the different steel samples and the extent of the flex, but not how easily not how stiff it is, but rather the extent of the stiffness flex. So anyway, well, this is quite interesting, this little clip of 2 or 3 years ago. I'm checking here, let's just start the video rolling. I'm checking here the pre-travel in one direction with a pair of scales, measuring the grams of force before trip, and I didn't push the button. Now we're rolling, and you can see it's coming on there. It's reaching about 110 111 grams to pre-travel in one direction. And if I just fast forward here somewhere about there, I think you can see I've just turned the probe around there to a different position, and now I'm checking the pre-travel in this position. And this was the big eureka moment for me, really seeing it graphically with scales, that in a different direction the pre-travel is much higher, getting about 150 grams in that direction. And that's the fundamental problem with these tri-swing arms, is that it takes more effort to more force in one direction than another direction. Of course, you might be thinking the tests we did in the workshop were in kilos. That was testing the material to breaking point, and the probes are only being used to tiny fractions of that, just for a few grams. So was it relevant, the test you're doing? Well, it is relevant, because they need to be able to stand a crash, and for an instant they're extremely highly loaded and you don't want them breaking. Also, it's an interesting test to compare the results, because while you might not be testing it to the same extent, the comparisons are very useful, and you can find the most stiff choice, or the most strong choice, or the biggest zone of stiffness choice that you're looking for. Because remember that pre-travel variation is the limiting factor on these probes. And some of the low-cost probes that I've been testing have a pre-travel variation of several thou. You know, we're talking 2 to 5 thou pre-travel variation, and I've been able to get the Hallmark probe down to a fraction of that. And while I'm here, here's a little clip on testing the Heimer. I was thinking of doing a breakaway stylus that could be re-extended after a crash event, but I stopped the development of this project because I could see that there would be long-term limitations to the whole concept. Anyway, here I'm measuring, see if I can get this going. Yeah, I'm measuring the load, and it's about 300 grams to reach the 0 point, and it starts to climb a little bit more, and then you get into the red zone. So let's have a look here now. We're coming into the red zone, and then it'll go up against a stop to protect the delicate internals of the Heimer. It's going to come on now a little bit further. It's hitting the stop about there, and if you were to continue beyond that, it would break the ceramic stem. And if you want to measure true stiffness, let's index over to the mild steel sample and put a position on the dial indicator, there, 0.3. This is just rough to give you an idea of it. We'll go in about the middle of there, from where the dial indicator is, and we'll pull on it a distance of 0.2. And that's taking about 3.5 kilos. That's a true measure of stiffness. That is how easily, 3.5 kilos is how easily the component bends. Now let's go over and do the same measurement on high tensile steel, and we'll find that we don't get the massive increase that we did with the strength test, because stiffness is a different quality to strength. Of course, I'm only approximating it here. I've got this roughly in the middle and so on. Now we're going to put on a 0.2, and that's about 5.5 kilos. So it is stiffer, and that's a good quality to have. But I just wanted to make it really clear that only now are we talking about true stiffness. And that's the stiffness that a probe should have, so that it has the minimum flex and the minimum pre-travel variation. Stiffness is a different property from strength. And some of you may be thinking, well, what about making the stems out of tungsten carbide? That is a really stiff material. Yeah, it's true. Usually stiffness is measured in Young's modulus, or the elastic modulus. And if you look at material property charts, you'll find that steel is very high, high tensile steel is very high, but tungsten carbide is off the scale. It's like 500 GPa. Whereas steel maybe 200 or 300 GPa. So I put a piece of tungsten carbide in here, and again, it's only approximate, and put the dial indicator on. Here we are, we're just setting it on 3, and put a bit of load on it. And we've got 10 kilos, and it's only moved 0.15. So that is a really stiff material, perfect for a probe stem. But here comes the classic compromise. You don't want it shattering if you have a major crash. You want to have and I didn't want to put more than 10 kilos on it then to get it up to find out just how stiff it is, because I felt like it's at the point of breaking. It's going to snap like a piece of glass at a certain point. And so it's not an ideal material. It's expensive, it's difficult to work, and it will fracture and not spring and recover. So while it might be suitable for some high-end applications, for general workshop use, it's probably not a good choice. Thanks for watching, guys. I hope you found that interesting. Cheers.